Yeah,
Right?
exactly. We're too far gone now. We're each like 200 games in. We might as well just finish.
I'm 300, you're like almost there.
Wow. Cool. You know, there would be, you know, to get enough data on something like that, there's different places that it might be interested. You wanted to write up something a little more extensive, that there's a journal called Chance, a magazine that does take contributions from undergraduates, and there's other journals like Quantitative Analysis and Scores, and a few other places that take things. So you get good enough data from this for an entire season that's unique in some way. It might be possible, you know, using it for more. So,
I was thinking, I bet like Nessun or someone does keep track of all this stuff.
I bet they don't want independent statisticians to do it because they pay people to do it.
Yeah.
Anyways.
No. I mean, like, I bet someone already has the data somewhere that we've been collecting. They just haven't like put it. On
So last time we considered, one thing we considered was distribution that came about from a normal distribution. Right? So if we had a bunch of observations and they're independent observations, like from a random sample from a population, and the data started out normal, like the measurements themselves are random normal. Then we said we do a few things. At the sample average over in the sum of the xi's will have a normal distribution as well. Its mean is mu, its variance is squared over n. It's more concentrated about mu. We did a couple other things. That a scaled version of the sample variance turned out to be a chi-squared with n minus 1 degrees of freedom. And you know, if x bar itself is normal, we standardized it. We can take z as x bar minus mu sigma over square root of n, just subtracting the mean divided by the standard deviation of this thing. This was a standard normal. But in statistics, we usually don't know sigma, so we have to do things like confidence intervals or tests where we estimate that standard deviation. And then this t, replacing this standard deviation by an estimated value, a sample standard deviation. This thing ends up having a t distribution, which is like a normal, but a little bit more spread out because we're replacing something known, a known value of sigma, by this estimated thing. And so we can do 95. This led to a 95% confidence interval for the mean. Was reported in all the articles that report confidence intervals for a single mean. Is the form x bar plus or minus some critical value, some 97.5 percentile from that t distribution, times s over the square root of n. Right? And that gives an interval, a lower value up to an upper value, that expresses what are the likely places that mu is located. What is the real mu based on our evidence of our data? Well, x bars are a good guess at where it is, but how certain are we about that? And the confidence interval expresses that. But what happens if the data aren't normal? These things were all probability calculations, all things determined by when the data are normal. Right? All the analytical results come out here started with this. But what happens when the data themselves are skewed, or there's outliers, or it's a mixture and not quite normal? Maybe we can turn off this overhead, the one overhead in the front. I think that makes it a little easier to see the screen. And so, but what happens if the x of i's themselves are not normal? For some distributions, you know, it's binomial, the same proportions, the sum is still binomial. And so there's various results that you can say in specific cases. But in general, you just go out and measure something in the world. You count something going on, You may take measurements on the trees that are around here, amount of sap that they produce in a period of time, and that distribution won't necessarily be normal. It might be close to it, but you have no way of knowing really. Right? And so that's where some limits come in. And often, if we don't know exactly what the distribution is, we can still say what the distribution of X bar is approximately. Limits and approximations. And so today, we'll look at some of the probability approximations that are out there that come from limits, right? So in calculus, there's limits, right? In calculus, the limits are things like what happens to 1 over 1 plus n as, what happens to that value as n gets big. And these limits, well, as n gets big, this gets closer and closer to 0. And so you're learning calculus, and that would end up being 1, right? As that number n gets bigger. You get other ones, you get things like the limit as, say, x goes to infinity, x over e to the x, script like the other one, right? This thing, well, x is going to infinity, e to the x is going to infinity, so that looks like it's infinity over infinity, but that's not something we do. There's this L'Hopital's rule where in calculus, where this limit is the same as the limit. You differentiate the numerator and denominator. As we differentiate that, it's 1 over e to the x, right? With respect to x. And so the denominator is going to infinity, so 1 over infinity, that thing's going to 0. So calculus has those types of limits of all sorts of things that go on, right? About limits of numerical sequences. Right? And what we're really talking about in probability is what's the behavior of a random variable as the sample size keeps getting bigger and bigger and bigger. Right? So in probability, we're going to have a sequence not of numbers, but of random variables that are progressing in some sense. Right. And what happens to this, what does it start to look like as you get bigger and bigger sample sizes? Is it going, as you get big samples, as the sample size, imagine you could sample infinitely long, would it approach another probability distribution? Not a specific value or specific number, but something in probability. So I can offer you one example, right? The t-distributions. That for a finite, for certain degrees of freedom, this thing's referred to as the degrees of freedom, is a little wider in its area than the standard normal. Right? But if you take a sequence of random variables, a t with 1 degree of freedom, a t with 2 degrees of freedom, a t with 3 degrees of freedom, etc. What is the limiting distribution? What does do the t-distributions look like as you get bigger and bigger degrees of freedom? Well, as this degrees of freedom goes to infinity, it converges to the probability structure of a normal, the standard normal, right? That excess variability related to estimating the unknown standard deviation, it becomes trivial because you have a big sample, infinite sample, you basically know that standard deviation, and there's no difference there. In pictures, the t with a small degrees of freedom, centered at 0, is quite spread out. And the tails, the probability content out away from 0, out of those tails is pretty heavy. But as you get bigger and bigger degrees of freedom, that it will become more concentrated in the middle and less down here. And then, you know, you keep going, it keeps getting more concentrated. And so this, so as the degrees of freedom go too big, you know, this curve, this probability density function, is the normal curve, is the one for the normal. And so as you get the t distribution, as the degrees of freedom gets bigger and bigger and bigger, it is the normal, right, in the limits. So probabilities for very large n would be very close to probabilities that would be from a normal distribution. And so we have this convergence, not to a single value, but to an entire distribution of value, probability structure. Right? And that's the big picture of what we're doing. There's two main ways we can look at this. One thing we can do, which is in 8.2, is called convergence in probability. So, for a definition, and if you have a sequence of random variables, I'll call them y because you get a sequence of random variables. These converge in probability to a constant C if for any little epsilon greater than 0, for any little tiny number you might think of or pick, the limit as n goes to infinity, as a sequence of random variables to find some how it keeps going, the probability that our random variable minus c is less than epsilon becomes 1. Now why is it n as we keep going? For the random variable. It's not just one value, it's a range of values, probabilities. But this says the probability that we're less than some distance from some number is 1. So we're sure to be very, very close. For any type of thing any type of caliper, any type of distance away from that we pick. That's the definition of convergence in probability. It's not just to a number, but the probability that we're close to a number. So it's slightly different from that. Where it gets used, and is useful for us, there's a theorem called the weak law of large numbers. There's a that says that let x1, x2, xn be independent random variables with mean mu and variance sigma squared that is less than infinity. There are random variables that have infinite variance. The t with 2 degrees of freedom actually doesn't have a variance. It's infinitely variable. So some things that the tails and the spread out in the extremes are so much that the variance isn't finite. Actually, you also get things that don't have finite variance by taking ratios of things that are close, that can be close to 0. So there's a chance that you're dividing by 0 or something very close to 0. Things kind of go haywire. But anyway, so these are well-behaved random variables like we most likely would measure in nature, right? And we let x bar n be the cumulative average up to that point. Right? This is the sample average of then for any epsilon greater than 0, you choose any little value you choose. Then the limit as n goes to infinity of the probability that x bar n is away from the mean. The chance that that is bigger than a little value is 0. And that the limit, conversely, that u would be that the average of the random variables would be less than epsilon when it goes to 1. So as you keep sampling and take bigger samples, the probability that your average x bar, the value you would actually see when you measure it, is very far away from the real mean u that generated the process, goes to 0. So you're very likely to be close to the real mean when you actually take samples. So let's take a look at a simulation, right? And then we'll talk about this is a theorem. It's something that can be proved, right? So if you're taking a class in proofs, it's going to look like proofs there. But we'll see how it goes. So in terms of simulation, right, let's imagine, sometimes it's called law of large numbers. Technically it's called the weak law of large numbers. It's a strong law of large numbers. It's more connected to real analysis and measure theory that says things are converged uniformly fast. It's the stronger form of the conversion. So let's imagine that we have data. And in this case, the data are going to be just binomial, or Bernoulli, really. Right? That we're going to imagine a genetic example where one parent contributes one allele and the other parent contributes the other allele. And there's big A and there's little a's. Right? And if you take, and if it's that type of Mendelian genetics, a quarter of the offspring would have from parent. So if one parent has a big A and a little a, their genetic type, and the other one has the same, they're both heterozygous. And it's just a random association, but a quarter of the time, they're both going to get the big A alleles there, right? So there's something that happens a quarter of the time and something that happens 3/4. Right? And I'm going to generate 1,000 values from a binomial. Each time is a sample of 1, so each person is either 1 or 0. And then I'm going to plot those x's over time. Right? So there's 1,000 people. Maybe the first one here is 0, so not capital A, capital A. All the ones at the top. Right? So it just bounces between, as you go along for 1,000 people, some are at 0, some are at 1, and it just kind of goes back and forth. Right? The version of the kind of the cumulative proportion over time is like the sample average. Right, in this case. So if we're taking the cumulative sum of the number of ones and dividing by the sample size, that gives the proportions over time. And if I plot those over time, right, so initially looks like I started at 0, then I got maybe a 1, and then another 1, and so, it's kind of bouncing around. But over the long term, that the proportion I have at any particular time frame, as I go along in time, the cumulative proportion over that long run is pretty close to the theoretical 1/4 that was used in the model, right? And so the law of large numbers is saying, because you're likely to be very, very close to that average over time. So that's one sequence. We can easily generate, here's a little loop, it will generate some more sequences. So these different colors are different sequences over time. And they start out with different randomness, right? Some are a little bit lower for a while. But eventually they all get back in here in probability. And so you could have one sequence that at any point, like at 1,000, it could be kind of far away from 1/4. But infinity is a long time. Eventually it's going to go so that you'll be arbitrarily close in there. Right? And so the weak law of large numbers says that the averages eventually get close in probability, and will be somewhere nearby. And you can do this with other examples. So say we had a multinomial with these probabilities that we're going to sample the numbers 1, 2, 3. Here's p hat 1, p hat 2 will be the proportions in the samples over time that are in the first category, second category, third category. And we can plot, this is one sequence, here's this other sequence, these are the proportion that were 1, the proportions that were 2s, the proportions that were 3s. They had proportions 1/16, 6/16, and 9/16. And all three sample proportions are going toward their kind of averages, that are these p's. You can do this with others. Here's a sample of gammas. The actual sample of gammas in this case, right, kind of looks like this, right? Those are a sample of 1,000 individual values. They're all over the place, right? The mean and variance are described there, right? That's the histogram. If you plot them over time, just individual values, there's not particularly a pattern, right? It's just each time point is a different gamma. And then if we start taking the cumulative averages over time and plotting those, right, they, have a little more variability at the beginning, but eventually they kind of settle down where they're kind of close by. And if you do this for other sequences, they have all their different starting patterns, whether it's the high values initially or some low values and things, but eventually that inevitability, the probability is converging. So that the values at the end, there's a little distribution. They're not all the same out here, but it's quite close. This is, I got kind of carried away and just did another example. So here would be a little mixture of distribution. So say N is a gamma distribution. Here's two different gammas with different parameters in here. One's a lower average, one's a bigger average. So imagine instead of having just one process, you have these kind of two things, and sometimes you get a sample from the first gamma that's low, and sometimes you get a sample from the next one, right? Maybe people are exposed to some infection, with injury, and if they're exposed, it takes them longer to get better. If they're not exposed, it takes them shorter time to get better. So there's kind of a mixture in there. For this one, if the average, this one, even though the data were these mixed things, kind of the average over time is still settling down. This would be the theoretical average from this is pretty much right on. And different things have, kind of settled down there. So the law of large numbers says that the X bar is getting close to mu in probability. Right? But we can also, this is a theorem, right? Empirically it seems to work. Our radar sense is you get bigger samples, it should be more accurate. We would know for an X bar of a particular size, from probability, we know that the expected value is mu, the average for all of those. And the variant, because they're independent, is sigma squared over n, or the standard square root of that. So we would expect the standard deviation to get smaller, kind of as a rate of 1 over the square root of n. But in terms of stating the theorem, probability theorem often deals in terms of proving these things. So I have a proof of this. Two of you had proofs or in proofs class, right? And so the idea of that, so, well, there's kind of a couple of ways to look at this, right? There is one result that's earlier in the book called Chebyshev's theorem. We didn't do much about proving it then, but it said that you have a random variable and its mean, the chance that any random variable is more than k standard deviations from its mean is less than or equal to 1 over k squared. And if for x bar, based on a sample of size n, if we replace that into here, the probability that x bar n minus mu is greater than k times its standard deviation, right? Its standard deviation is sigma over the square root of n, which should be less than 1 over k squared. And our result, right, says, you know, what we're doing in terms of the theorem is we're not necessarily tied to this thing. Just pick some small number, 0.01, 0.001, any small number you like. We want to show that as n gets big, that the probability that x bar n minus mu is greater than equal to alpha is 0. That's what we want to show. And so the way that this works, once you have Chebyshev's result, is we're going to pick our epsilon. You pick an epsilon, and I have to show that it works for that. I'm going to set that, where it is, I'm going to set my value of k there to be epsilon times the square root of n over sigma. Oh, nice choice of k here. Right? So this was because of Chebyshev's result. So if I pick that there, this Chebyshev's result means then that the probability that x bar n minus mu is greater than, well, we put this thing at epsilon, right, is less than or equal to 1 over k. Well, k in here, 1 over k, there is epsilon squared over n. That goes in there, and sigma squared is there. So how did that happen? I took this equation. If I plug this version of k into there, k squared, so I get the numerator squared, it's in the denominator, and the denominator squared is the numerator, is the 1 over. And putting this in for k, right, the sigma over square root of n cancels those. So I end up with the probability that x bar minus mu is greater than that is less than or equal to that. Now, what happens as n goes to infinity? What happens as the sample size gets really big? So the limit of this thing x bar n minus mu greater than or equal to 6, right, is less than or equal to the limit as n goes to infinity of this thing. But that little epsilon was the number you chose. It's 0.01, 0.001 or something. And sigma squared is just the variance, right, which is we assume to be finite. And so that thing's going to 0. The limit of that is 0. So the chance that x bar minus mu is bigger than some value is basically 0. So that's the weak law of large numbers. Right? Once you have that Chebyshev thing, it's a few key choices about things. Right? So we pick an epsilon. We want to show this. Once we pick that epsilon, we make that nice choice there. Chebyshev's inequality gives us this result, and then the limit follows there. We didn't exactly, yeah.
Is it because the epsilon is so small?
Well, the epsilon can be small. The reason it's going to infinity is because we have n in the denominator down there. Right? And because n is in the denominator, the limit of that number, right, this is kind of a calculus limit, right? Sigma squared is a number, epsilon's a number, and this. So this calculus limit is 0. So our probability is small, and that illustration, you know, all those curves starting from different places eventually end up at the same place at the. So we didn't prove that Chebyshev's result. It's, you know, if you have started a project and wanted to do and like groups and that sort of type of thing, there are a couple ways to show that Chebyshev's inequality. So some parts of probability get very much into the proofs of inequalities and results like this. There's something called the Markov's inequality. So if y is a positive random variable, meaning that the only values you can take on are positive, you can show that the probability that a variable is greater than some value, right, is less than or equal to its expectation over that value. And this thing is not too bad to show. What's the expectation of a random variable? Well, it's an integral over its space of, with its density. You could also set this up for a discrete random variable. But if it's a positive random variable, this thing ends at 0. And you know, y is positive, the density is positive. So this thing has to be greater than or equal to that integral stopped at 1, at some value. If you cut off part of the integral, and it's all positive, right? You've made it smaller. And then if you, this thing also has to be greater than, so y in this integral is getting bigger, so a up to infinity. So it has to be bigger than a times that density. And this one, the a can be pulled out. Because it's a number. If you have a density of y and you integrate from a on up, that's the probability that y is greater than a. Or greater than or equal to, either way. So we started out with the expectation of y and did a couple little tricks there to get inequalities. And ended up with this thing. So, right, so then that means the probability that y is greater than a, well, this is on the lower side, right? This is less than expectation of y. You could divide by that value of a. And that's something called Markov's inequality related to probabilities. Now, a certain choice of things. There's other ways to show that a project might look at what other way of doing that if you're interested in that. That if you make a certain choice for y, right, basically y minus mu squared, you get something positive, and then everything will kind of go through. So so the Markov's inequality. The probability that y is bigger than some value is less than the expectation, and over that value. And now we're going to think about some random variable x. We're going to let y equal x minus mu squared. This is a mu. That was like an a. See there? And we're going to let a equals k times sigma squared. So x minus mu, right? We're interested in that in law of large numbers, difference between x and mu. Right? Squaring it, it's positive. And we wanted law of large numbers to have k times sigma, right? K times a certain value, right? So this thing says the probability that x minus mu squared, right? So plugging these things into Markov's inequality. This thing has to be, right, that is greater than, left out part of it, that is greater than k squared sigma squared is less than or equal to, well, now the expectation of y is x minus mu squared. And a is k squared sigma squared, right? So that's plugging in. Now, everything's here positive, right? And we can take square roots. That probability shouldn't change. So this is, take the square root of both sides. If x minus mu squared is bigger than that, then the absolute value of x minus mu has to be bigger than that square root. It might be negative, x might be a negative random variable, so you have to have expected value in here. That doesn't change. What happens on this side? What is expectation of x minus its mean squared? That's our variance. Right? A random variable minus its average squared is variance. The variance of that is sigma squared, or just a random variable. 1 over k squared. And this is Chebyshev's. Inequality. And then we started with Chebyshev's chart inequality and then did the weak law of large numbers. So this kind of, we start with Markov, then Chebyshev, and then the weak law of large numbers. We get this convergence in probability result. Right? But any questions? So if your math major is interested in proofs, this is some useful proofs. Some advanced study of probability theory would go more in this direction than the other stuff that we've been doing. Study some of these. Right. There's a journal called Annals of Probability that most of the articles would be proof-like articles. But what we've done, the big result, the weak law of large numbers, is that we have the xi's, if they're independent with each other, each one has expectation mu, and the variance of each one is sigma squared, that's finite. Then x bar in converges in probability. To its mean. And so that's one sense of convergence that's important in probability theory. But any questions? I was afraid that I was going to say, oh, integrity's about done. We haven't gone that slow. But anyway, any questions about? So that's one thing that gets looked at, right? You're converging to the means. Other things that are transformations of the means have nice convergence probabilities too, but we're just going to do this one for now. The other main convergence is entire probability distribution. Not only is it converging to be close to a mean, but what's the spread and what's the probability? So the second main one, which is in 8.3, is called convergence and distribution. So a definition of what this thing is, convergence and probability distribution. Right? If xn is a random variable cumulative distribution function Fn of x. And we have these for a sequence of random variables. In the first random variable, second random variable, etc. The application we'll do with x bar is we have the first value, and the average of 2, then the average of 3, and the average is going forward. And x is another random variable. With cumulative distribution function f of x. So this is the definition. Then x sub n, the sequence, converges in distribution. To x if the limit of Fn of x that then goes to infinity equals f of x at all x where f of x is continuous. And this f of x is called then the limiting distribution. Of the sequence. So if the CDFs that you have initially, right, as you accumulate more and more data, or as you go further and further in the sequence, if they start to look like and eventually become numerically equivalent to the cumulative distribution function at all the x values that are possible, except where it's continuous, then it is that distribution. It has that probability distribution in the limit. We call it convergence in distribution. So you kind of a sequence of binomials or something, and it's going to converge and look like something else, right? And it's through this process that we get results for things, and we don't exactly know what was underlying it. It should start looking like other things. Right? That's the definition. There's one theorem that we'll use, theorem 8.3, that will state. Right? So if xn is a random variable, and it has a moment generating function, and x is a random variable, and it has its moment generating function, if the limit as n goes to infinity of the moment generating functions is equivalent to this other moment generating function, then the random variables xn converge in distribution to x. So sometimes you can prove this convergence with the cumulatives, but the one example that we're going to, a couple examples that we're going to look at, are easier with moment generating functions. Right? This is proof is not included in the book. It's a lot more calculus about making that work out. So we're just going to take it as something that we know and look at as an example of how this works. So if the sequence of random variables, each one has a moment generating function, and as time goes on through your sequence, if it ends up that if n would go to infinity, that function would turn into this other one, then you have a new random variable, and that's where it converges to a distribution. So here's one example. Say x sub n is binomial with some n and p. The moment generating function for this binomial is p times e to the t plus 1 minus p raised to n power. What happens Does it start to look like anything else? Does it converge to any input and distribution to something else we might like to use? Well, let's suppose P is small and let lambda equals n times P. Then we can rewrite this moment generating function a little bit here. The whole thing can be rewritten without using that lambda as 1 plus, see there's the 1 there, and then there's a p e to the t minus 1. We can take this p from here and just group it with this one as some step. And p, so this means here as well that p equals lambda over n. And we're going to plug this lambda into this one up here. So we get 1 plus lambda over n times e to the t minus 1, and all of that to the n. So what happens to this thing as n gets big? Now, calculus, there's a limit. There's a limit equation. The limit, if you have a limit as n goes to infinity of 1 plus some number over n is e to the k. That is one limiting relationship. And so, kind of the analogous of this part, we're going to let k be our e to the t minus 1. Oh wait, no, lambda has there, right? And so if we take the limit of that thing, as n goes to infinity, of this moment generating function, that's 1 over something over n. Okay, our something is lambda e to the t minus 1, and it's raised to the nth power. So then we get e to that thing. So we should get e to the lambda e to the t minus 1. Does that moment generating function ring a bell? Did that look familiar?
Exponential.
It's close to exponential.
Gamma.
Poisson.
Dang.
So if x is Poisson lambda, then it would have that moment generating function. So this application of the convergence distribution, right, says that a binomial distribution where the rate is n times p. So if p is small, you're thinking p is a small number, and n is getting bigger as that's held fixed, then that binomial is close to Poisson, right? Convergence in probability or in distribution to Poisson. What that means in practice is if you need to compute probabilities for a binomial with a huge number of trials and a very small rate, right, that you could convert it to Poisson, compute probabilities, and it would basically be the same. Right? So for instance, if, so for example, we have something where n is large and p is small, and we have, x of n is binomial np, then it's approximately equal to Poisson with rate lambda equals n times p. So for instance, if n is 100 and p equals 0.01, kind of a small rate, And the probabilities we calculate with the binomial formula are going to be almost exactly the same as the probabilities we calculate for a certain number of outcomes under the Poisson. The expected value over here is 1. The variance over here is n times p times 1 minus p is 0.99. Over here under Poisson, right, the expectation of that one is 1, and the variance is 1. So it's a little bit different, right? Probabilities will be off a little bit, but they're quite close. And in particular, a lot of applications in public health where you're dealing with a rare disease or fairly rare occurrence of something. You have 50,000 people in a county or 1 million people that might be exposed to something, and a few hundred or a small rate have that. You know, it's really binomial, because you're counting the number of times something happens out of a group of people, so it's probably binomial. But often the modeling and the testing and everything is done with Poisson, because the limiting distribution is Poisson, and the approximation, pretending for certain numbers that it is Poisson, is quite good. Modern computers are, it kind of makes it easier to use exactly binomial, because it's easier to put big numbers and everything into computations quickly. So it's a little bit less of a savior, but it's still the limiting distribution, and so in very large cases it would still be relevant. But there's tons and tons of other examples where this type of thing works out. So if xn is binomial in P, right, converges to a Poisson for lambda equals np. And generally, P is things being has to be small, because if n is getting big, to have a constant lambda, then you need it to be toward bound. So Poisson lambda, that Poisson, as described in this book, as the lambda gets big. So how does Poisson, take one Poisson, you add it to another Poisson, you add it to another Poisson, right? Take the average of those. The Poisson converges in distribution, a little d for distribution in here, to a normal random variable with rates of lambda and a variance of lambda. So there's other things using moment generating functions. Like as you get t's, they become like normals. As you take averages of, take a chi-square, you're adding things together, a series of chi-square with 1 degree of freedom, 2 degrees, and so on. Initially, it starts out very skewed. But as you get more and more larger and larger samples, right, as the degrees of freedom, chi-square 1, random variable chi-square 2, random variable chi-square 3, random variable. Eventually that goes to a normal random variable in distribution. So there's lots of ways that different distributions are related, and sometimes we can show it with these kind of moment generating function type arguments in one way or another. And so convergence and distribution, that you start with one distribution, and under the conditions of infinity, when it's getting big, the probability structure, all the means, variances, probability calculations are virtually identical under that other distribution. Right? The big result that comes out of this type of convergence is simple limit theorem. Which is probably among the most useful things in statistics and probability, right? So this is a theorem. It's theorem 8.4 in the book. So we're going to let x of 1, x of 2, x of 3, right, be up to x of n, be independent random variables with mean mu and of n times x bar minus mu over sigma. Another way of writing this same thing would be x bar minus mu divided by sigma over the square root of n. I point this out because sigma over the square root of n is the standard deviation of x bar. Right? So we talked about the variance of x bar, sigma squared over n. Right, so it's taking this difference and the standardizing. If you flip it, flip this thing up, right, it looks like that. That's right there. That this thing converges in distribution. To standard normal. But the probability distribution for this standardized version of x bar becomes normal in distribution. So you can use normal probabilities to calculate areas and means and variances of everything else, or whatever else. But the amazing thing about this is it doesn't say very much about what x has to be. X doesn't have to be normal to start out with. It doesn't have to be symmetric. It can be skewed. It just has to have a mean and variance. There's versions of this that relax some of these things. Like they have to have kind of the similar means, or and they have to have kind of similar variances, but no variance could be too extremely big to throw things off. Right, so and it could be a little bit. They don't necessarily have to be independent. There could be slight correlations, but the correlation can't be too big. So there's many versions of this that relax assumptions, but the basic assumptions you just have to have a mean and variance. And these can be anything. They can be discrete, they can be continuous, they can be skewed with outliers. But still, the distribution of x bar standardized comes out to be like normal 0, 1. So it's just amazing, it's kind of amazing because things can be really skewed and look completely chaotic, totally different from normal. But the averages end up being this. So let's look at a little simulation for that. So a gamma, so if you do a histogram of random gamma random variables, say you do 1,000 of them, with 5 and 2. Right, that histogram, well, it's a little skewed to the right. Let's take 1,000 samples of size 20. Right? And then take the, put those together. Right? So here's our 1,000, here's 20. And then get some data. This thing, the first row, right? I guess I'll just show you the first row. I just do the first row instead of the first 3 rows. The first row, oops, flip it off, right, is the first 20 values. Right? The second row is the next 20 values. And so there's 1,000 rows, each with 20. And if I take the average, by row, each one's an average of 20. Right? Each 20 values looks kind of like the gamma. It doesn't look normal necessarily. But let's take the average of 20. What does the average of 20 look like? A little bit more normal. There's a little tail out here, a little bit skewed, but it's much more normal. If we do it on this scale, we can put the normal probabilities on it. Which normals did I put on there? I took the mean and the standard deviation from that gamma. And said here, I'm going to make it normal, but use the mean and standard deviation from the gamma. And it looks pretty close. Right? If you do the normal probability plot, you think this thing should be straight. That's not bad. Right? The normal probability plot, if I go back and figure my original random sample somewhere. Right. So if I do the QQ norm of just the gammas without taking averages, 1,000 values, a little bit more of a bend with a little bit out here on the tails, a little bit less normal looking. But the average is at 20. It's begun to straighten out. What if we do 40s? Here's 40 of those. Here's the histogram of 40 averages. Averages based on 40. There's 1,000 averages. Each one is based on 40. Right? That should look a little bit more normal. Right? Here's the probability version of things. And this one looks pretty straight. What if you start with something that is a little further away? Right? So this thing will generate my mixture. So my mixture that I did before had a big clump at the lower end and then a higher clump up here. So my individual values here from that first row, I can just do a histogram of all my data, just thousands of those in there. That's what the distribution is that I use to simulate the data. And the QQ norm, that isn't going to look normal at all, right? Because of this mixture, there's a gap in the middle, so it's not straight. But what about the averages of 20? This is averages of 20. Right? The averages of 20, pretty much symmetric. So this is 1,000 averages. The normal, a little, but mostly straight. Mostly looks like normal, taking averages. Well, these are kind of artificial ones in the sense that I've started with some probability model, so I know it had mean and variance and things. What if you do this with something more like real data? So that's that data set. Looking at the 50 states, right? The histogram of their areas is extremely skewed, right? Alaska's huge, and California and Texas and a few other places are really big, and a lot of them are much smaller in comparison. So there's this massive outlier, it's skewed. If we do, say, 10 classes, right, it looks more like this. So it's skewed, a few outliers in there. If we take a sample of 1,000, we could, that's just a sample of 1,000, it's 50 points really, but I'm in the population, I'm resampling 1,000 times, right, independently, so we'll get replications and everything. This, I guess, is looking at really the law of large numbers, that if you resampled from a distribution like that, right, and plotted it, the average, as you get more and more, is going to get close to the average area of these 50 points. Right? So the mean of 50, mean of the areas is there. So that line. And resampling is going to get you close. But what's the distribution look like? Let's pick 20 of the states and do that 1,000 times. And then take averages of 20. So average of 20 samples. And the histogram looks like that, right? At 20, this one still looks a little bit skewed, right? Sometimes you get that big outlier, one of those two big outliers, and then the average of 20 is a little bit higher. Sometimes you get, if you did independent sampling, you could get the very biggest one twice, right? But more likely, you're more likely to get a bunch of the small ones if you do that. Q norm plot is a little warped. Right, that because of the skewness, these are a little bit big, right? So it's a little warped. What happens if we go up to 40? Right. Here's the histogram at 40. Maybe still a little bit of a tail out there. What if we resample 80 times? Maybe it's looking a little bit normal, or 120 times. Yeah, well, maybe there's just a couple outliers, but most of it looks quite straight. Right? So if we do this normal, it's, where's that other one? At 20, I think this one was. This one had a pretty big bend. But as we've gone along and increased the sample size, I think there's still a little bit of a bend there, but not nearly as much. Right? And so whatever the distribution is, that you're starting with, right, then this transform value, as long as n is right, is getting big, and going to infinity, the limit is that it gets very big. As it goes to infinity, it goes to normal 0, 1. The way this gets used in practice, right? So if y sub n is square root of n times x bar minus sigma, if that's converging in distribution to a standard normal, we think about x bar being approximately distributed, approximation for large values for large n, as normal u sigma squared over n. So whatever we started with x, it could be binomial, Poisson, some arbitrary thing out in nature that the sample averages get close to normal. Right? So if you wanted, say, the probability that anyway, if you want probabilities, you calculate probabilities. If you want to do hypothesis test, you can do hypothesis test. So, as an example, say you are measuring lengths of beaks on American meadowlarks. And let's say that the average of adults is 2.5 centimeters with a standard deviation of 0.2 centimeters. And we take 40. What's the probability that we're going to get an average more than more than 2.7 centimeters. So initially, we don't know what the distribution of these things is. Is it normal? Is it somehow skewed or funny? Are there ones that are very large and some most are smaller? Or is it kind of a mixture of dominant, non-dominant ones of some sort? Are there mixtures by, there's 1-year-olds, there's 2-year-olds, there's 3-year-olds? Is there kind of age-related things so that survival, they don't, the ones that if some species keep growing throughout their lifetime, and maybe there's some effect that after a few years their beaks get longer. Gravity has its effects on things. So initially we couldn't calculate this probability because we don't know what the distribution of x is. We can't do much. Right? But x bar should be approximately normal, centered at 2.5, and the standard deviation for x bar should be 0.2 over the square root of 40. And so the probability that x bar is greater than 2.7 centimeters should be approximately the chance that a standard normal, you subtract the mean, divide by the standard deviation, to get a normal value, and then look up that on a normal probability table or through the computer. That is, use the normal distribution after standardizing it. And it's the central limit theorem that makes this a reasonable approach. Smaller, pull it over here. And, for now, that out. So if we want to do, and this is I really want, the 2 point, here this x bar, this thing to 2.7, right? We actually are concerned with this number. So that's subtracting the mean and dividing by the standard error there, standard deviation, x bar. So 2.7, oops, holy cow, I typed on there, huh? 2.7 minus 2.5 divided by 0.2 divided by the square root of 40. Right? Oh, not sure why that's, must not like the fact that I made it small. That ends up being 6.3. So I've made up a little example on the spot here, right, where we're going to get d greater than 6.3. It's basically 0. If we chose a more reasonable number, and what's the chance that x bar is greater than 2.55 centimeters, is about equal to the probability that a normal is greater than 2.55 minus 2.5, 0.2 over the square root of 40. What's the chance that our average is greater than that number? It's the same thing. If the distribution is not too extremely skewed, I wouldn't expect it to be for length of adult beaks, that, then it should be approximately normal. So if we subtract the mean divided by the standard error, that's 1.58. The chance that a normal, standard norm is less than 1.58 is about 94%. So the chance that we're bigger than that is 1 minus it, or about 6%. So, yeah. Well, I guess there's not too much space to write that. This thing is the probability that a standard normal is greater than 1.58, which was 1 minus the 0.954, I believe. 943. 1057. So just about 6% of the time, if you took a sample of 40, it would be bigger than 2.55 centimeters, if you're interested in that probability. And so even though we don't necessarily have any information of an average and standard deviation, even though we don't know that it's exactly normal, it could be whatever it is, that the probabilities from the normal calculation, because of the central limit theorem, should be pretty accurate. And usually in intro textbooks, they say x bar is approximately normal if n is greater than 40. Is the general advice that they give. Maybe sometimes some people say 30. Is that terribly good advice? It sometimes works, sometimes it doesn't, right? If the original distribution of x is highly skewed, x bar is not going to look normal just based on 20 to 30 or even 40 observations. If it's skewed with outliers, you probably need 80 or 100 or more to make x bar look roughly normal, right? So really, there's a sliding scale. If x, the xi's, if they're approximately normal to begin with, you don't need many at all. 5, 10, 15 probably is fine, right? At the other end, xi highly non-normal. Right? You need then really big to make this thing work out. And the 30, 40, a lot of things you measure in nature or might be used in examples might be, this is might work for many things, but the advice is to look at the data. Right? Does the data look like something that's not too skewed? Now, if it is highly skewed, right, we want to start with data that are closer to normal. So some things like this area, one response to it being so skewed, so let me get everything back up here. The histogram for the area variable was like that. If you take log of every value, right, the distribution is like that. That doesn't look normal. It looks like there's a lot of small values and a couple big values. But it's a little more symmetric and not quite as spread out. Right? It looks closer, right? So doing things on the logs scale, right? Taking a sample size 20, and then taking 1,000 samples of size 20 and making some histograms, taking the averages. This is what it looks like. The distribution of X bar looks like that in simulation with 20 when I do everything on the log scale. Because it looks quite close to normal, right? And if you, I think that this looks pretty straight, pretty close to normal. The original one with 20, back up here, if you recall, was pretty distinctly skew right. And probabilities calculated, assuming this is normal, just won't be too accurate. But on the log scale, 20 seemed okay, right? A little difference from normal, but we're pretty close, right? So if you start with something that's closer to normal, that limit of the central limit theorem, you get closer to normal faster, right? And part of advanced probability theory is what considerations you can do analytical work to try to figure out rates of convergence. How fast is it going towards normality? And what's the difference? You know, it depends on skewness. And kurtosis is a measurement, you know, the fourth moment about how heavy the tails are is related to that. So it's kind of a sliding scale. So returning to what, you know, this confidence interval idea. So if you have a set of data, independent sample, independent measurements on measurements. And the n is not, n is, you know, is moderately large. And the xi is not too skew, not, you know, few, you know, extreme outliers, which is not there's not an enormous one out there, right? Then X bar is going to be approximately normally distributed. And a 95% confidence interval for the mean using the t distribution, which is the special adjustment for estimating the variances in the normal case. Right? Should work well. Even if the data themselves weren't normal, because of the central limit theorem, confidence intervals should give you pretty good performance. Meaning that if you make a bunch of intervals in different, you know, over your lifetime, over your career, and they're all 95% intervals, about 95% of them should be accurate. Some will miss, some will be accurate, but even if the data were not normal, probability theory says the distribution of X bar in large, moderately large samples is approximately normal. The theory is that the limit, as it goes to infinity, it converges in distribution to that normal, but it gets used in practice that you're able to do calculations in cases where the combinatorics and all that would be just really kind of a mess, fairly simply, based on the normal. So we're looking at limits. Many times you have a small number of random variables and putting them together. You can actually go through those transformations, maybe use moment generating functions, and figure out what the new distribution is and get exact results. But in a number of cases, as the sample size gets big, things converge in probability or they converge in distribution, and then you can use those distributions they converge to give you accurate ideas of probabilities and so on. And The big application is the single limit theorem, because it's the core underlying support for everything that goes on in confidence intervals and using normality and so on. Part of statistics is called non-parametric statistics that tries to get away from using normality and relying on that to do other ways of doing inference and saying things about a population from a sample. But by and large, a lot of things use this type of formulation, adapted for new data structures and new estimates. Right? So, any questions? Yes.
Is there gonna be one more homework assignment?
Yes, and so I would hope today, or at least by tomorrow morning, we've had probably just a couple problems, so a little bit shorter. Just that one that would do a little bit with limits, and a little simulation, and maybe one or two problems out of that. And so shorter than the other ones that have been done. I know you're looking at projects as well. Next week, on Monday, we'll talk about what's on the exam, what's going to be covered or not covered, time for questions. Wednesday, the last day, will be more time for review problems and so on. So we will, the homework will get posted, a couple of problems to do, and then we'll do review. I do have the homework. Yeah, we should. Huh? You. Thanks.
True, right, my
I don't know, that one that you spent hours on the bonus problem.
Oh, true. That's my Mona Lisa. This will be. I can't think of a lesser Da Vinci.
Yeah, I don't know, that's probably.
This would be the like contraption that you made, the like.
Yeah, the one that no one ever really noticed.
No, the like flying thing, didn't you?
I thought he designed one. I never built it. I'm not
Yeah,
sure.
exactly.
You're size of that call today?
Yes.
Are you heading straight now?
Pretty much, yeah. I'll be able to soon. I'll just take this and then.
All right, thank you, Mom.
Yep.
Describing the discharges. Yeah.
Thank you. Yep.
Did you get this one done?
Oh, okay.